Room-scale virtual reality is becoming very popular, but a challenge for traditional room-scale virtual reality is a lack of haptic or physical feedback. Without this feedback, users penetrate virtual surfaces, which reduce the immersive quality of the experience. Our approach is to use a system of autonomous robotic props that dynamically reposition themselves on an as-needed basis, known as ZoomWalls. ZoomWalls provide haptic feedback for represented virtual structures. Each zoom wall operates in one of three states: active, standby, or dispatched. An active zoom wall represents a virtual surface. A standby zoom wall waits to be assigned to a virtual surface, and a dispatched zoom wall is one that is on the move to materialize a virtual surface. A tracking system uses real-world information about the user's position in relation to the virtual surfaces in the environment. It uses this to predict which surfaces a user might need to touch. When it has determined which surface should be touched, tracking system information about the position of zoom walls is used to figure out which zoom wall is closest. The closest standby zoom wall is then dispatched to the target location so that the virtual surface can be materialized. In the debug view here, active zoom walls are blue, gray zoom walls are on standby, and yellow zoom walls have been dispatched. When users move away from a virtual surface, the active zoom walls go back into a standby state. One challenge is to predict which virtual surface will be touched. We explore two prediction algorithms. The first is a naive bounding box where any virtual surface within a bounding box around the user is predicted to be a surface that needs to be materialized. As the user moves around, a bilaterally symmetrical bounding box of 300 cm by 150 cm follows them around. Surfaces within that bounding box are predicted to be touched and are materialized by the zoom walls. With 3 zoom walls, we can see the system is fairly responsive. But managing 3 walls is tough. The possibility of colliding with one of these zoom walls accidentally is higher. The next challenge is how to simulate the whole room with fewer walls. Unfortunately, our naive bounding box algorithm does not work well when we only have 2 zoom walls, and creates significant latency that degrades the experience. So we explore the second algorithm, which uses support vector machines. Based on the training data, we try to predict which virtual surface the user is going to touch in a fast and accurate way. Simple training was done to get ground truth about users' motions in relation to the different surfaces in the room. Here, the light blue highlight is the predicted surface from the bounding box algorithm, and the green surface is the surface that's been predicted to be touched by the SVM. This surface is given higher priority in the zoom wall system. With this algorithm, we can see that 2 zoom walls effectively materialize the virtual walls without substantial latency. In this simulation, we test both algorithms working with our zoom wall prototype. From the video, we see that there is very low latency with this combined approach. We created a first-person shooter game to explore the zoom wall concept further. Here, 3 zoom walls work together to provide haptic infrastructure for the environment. Here, the user takes cover behind the corner of a corridor, where the zoom walls represent the corner and the walls of the corridor. The user can use the zoom walls to physically hide from the shots of the bad guy. At the end of the corridor here, the user opens a sliding door, represented again by another zoom wall, showing that we can represent a wide range of haptic infrastructure. We created a cliff scenario where a user moves through a narrow path with a cliff wall. Here the user walks slowly while continuously touching the wall, something that takes advantage of ZoomWalls' capabilities. We briefly show our explorations for different kinds of rooms using 3 zoom walls with the bounding box plus motion ML predictor, which was shown to be best from our simulations. Here the 3 zoom walls can be used to represent a narrow corridor where all the walls, the sides and the front, and corners are fully materialized by reusing 3 zoom walls. Second, zoom walls can represent a zigzag-shaped room as an instance of a complex maze-like environment. Our algorithm using Motion ML can be applied to a 4-wall room unit and sequentially applied to predict priority walls that might be touched, which can materialize necessary wall components in a whole room. As shown in this video, while small positioning and rotational errors exist due to the tracking system, zoom walls can be located smoothly without significant delays. Zoom walls can be extended by changing the size of the physical props on the surfaces, as well as the materials and textures on them. They allow us to simulate haptic infrastructure of virtual reality worlds effectively.